So let's look at multiple writers. Okay, things get more interesting now. So far we had a proposing general and a following general. Then we had a proposing general and a thinking general who said, I agree or don't agree with you. And now we'll have multiple proposing generals. Okay, so the reason I didn't go and show those traces is because, as you can imagine, it would get messy. So they both send different orders to each other, and now their values are inconsistent. So how to solve this problem? And as you can imagine, we can have a coordinating general. Okay, so and let's say this is the coordinating general. So he proposes dusk, and sorry, he had dusk. He proposed dawn, but he got dusk again from the other general. So he can just go and say, okay, I know I've got two values proposed, dusk and dawn, and I'll choose maybe the second one. So he goes and sends dusk to the other person, and then they know that this is the committed value. Okay. So here the coordinator chooses one value and rejects or aborts the other value proposal. Okay, and in this case, he rejected his own proposal. Okay. So I use the word abort or reject. Okay, so time for a question now. You probably have heard the word abort earlier, and abort is a technical term in computer science. There are other terms that go with it. So I'm just curious. We'll talk a little bit about this issue. This concept is learned in several other kinds of courses in much more depth. But if you're going to talk about multiple writers, we can't get away from talking about aborts. Okay? So try to imagine what this might mean and what other concepts might go with it that you know about or can think about. Okay. So let's go to that question. So let's look at this concept in more depth, and we'll see where abort falls. Okay. So let's go and see the various alternatives we had. Okay, abort was one of the alternatives, and we'll talk about what abort really means soon. But let's go and talk about alternatives to abort also. And like Leo said, abort comes with undo, but we may not abort always. So we're going to talk of three kinds of concurrency controls, and this particular box has appeared earlier than I intended it to. So in one case, what we can do is we can do non-atomic writes, concurrent writes. Okay, so if the original state was S and some command C1 arrives and another command C2 arrives also at the same time. Okay, so let's say there's one process that goes and executes C1, another process executes C2. They can simply go and execute that at their processes, send the command to each other. So the first process executes C1, then does C2. The other process does C2 and then does C1. Okay, so here we're talking about non-atomic here, which is that we are not going through a central process. Okay, central process was one way to make sure bad things don't happen, but bad things don't always have to happen when there are multiple writes. And when bad things don't happen, we don't really need a central process. So it may be such that the kind of commands we execute don't require a central process, and yet, which means they don't require what's called atomicity, which means that the commands can be executed in different order at different sites, and things may still be fine. Okay, that's one alternative. Here are the other alternatives. C1 arrives, is issued by one process. C2 is issued by another process. They are serialized by some central process. So now we are using a central process. And both of them are executed. And first, let's say C1 arrived. So C1 is executed, and then C2 is executed at both sides. Okay, so this is atomic. Each site is executing the same sequence of operations. Here, each site is executing the same set of operations, okay, but in different orders. And here's the abort case that we saw in the multiple in the coordinating general example, that C1 is issued, C2 is issued, And before consensus is reached on C1, C2 was issued, so that's why they're concurrent. And one of the two commands is chosen, and the other command is undone or aborted. And this is what's called, and when you do this, we have serializability. Okay, so this was a term I was looking for in conjunction with abort. Okay. And so a question that arises at this point is, this seems safe. Okay. Maybe this is safe. This seems definitely unsafe. But I'm going to argue that depending on the application and the set of commands, all three could make sense in some multiple writer reader cases. Okay, so think about that. I think that's my next question. Okay. Why does each of them make sense sometimes? Okay, so that's my next question. Okay, so you guys gave examples from the project. I gave examples of graphical objects where you've got a color, maybe color and position of an object which has multiple attributes which are independent of each other. But let's just assume a hash table like data structure where we have delete, but we also have replace. Okay, so replace is not the same as put. Put, if it doesn't find a key, it will go and associate the new value with the new key. And the key exists, it's going to replace the new value with the old key. Okay. So if this is the case of an object having both a color and position, let's say. Okay, so the object has got one property that's K1, another property that's K2, and we are changing the two different properties. So it doesn't matter in what order we do that, and this is not atomic. Okay, and with the Andrew's example of move, we might be sending relative offsets, so two moves add up. If you say first move forward 2 and then you say move forward 3 units, then whether you do 2 first and then 3, or you do 3 first and then 2, the result is the same. Okay, so this is the non-atomic case. Here, this is the general case, that we are dealing with the same property, but we have two different values, and we'll choose the value that of we'll choose one of these values and the value chosen will be the one proposed by the last command we execute. Okay, so C2 is the last command we execute, so that's the value we'll agree on. And here's the case where we've got one command that says delete this property, and the other command that says replace the property with this new value. So imagine you're in a directory, and one command says delete the file, and the other command says replace the file with this new value. Okay. So there's inconsistency here, because if you do this schedule, then we might do the delete before we do the replace, in which case the replace will just fail. Okay. And so what we want, so this is so to make it serializable, we need to go and choose one of them, because there's a dependency between these commands. Okay. So that was the key, that here there was no dependency and here there is dependency. Okay, and in general, this problem is hard because we don't know what the set of commands available are. Okay. And so we need to provide some concurrency control mechanism that is type independent. Okay, so we can support these 3 type independent concurrency control mechanisms, and then some particular application will say, okay, I want this suits me, or this suits me, and so we can choose among these. Okay. But the concurrency control algorithm is not trying to figure out whether 2 commands commute or not, and whether there's a dependency among these commands or not. It just goes and does things in an application independent or type independent fashion. So what does or might abort mean in CS, and what other technical terms go with it? So the word transaction is something I use when I talked about Travelocity, making reservation through Travelocity, where you need to book a hotel, you need to go and book a car and an airline. Okay, and if one of those commands aborts, then as Leo mentioned, you have to go and abort everything that transaction did. Okay? And transactions, what are transactions? How are transactions different from any sequence of commands? They have what's called the ACID properties, and the I in the ACID means isolation. And isolation means that if you have a bunch of concurrent transactions, then the result of executing these transactions concurrently is the same. And generally, the actions are read and write. Okay, though we can have type specific actions also. So the result of executing the concurrent transactions is the same as executing the transactions serially. So when we abort a transaction, we are essentially saying that that's not in our set, and so we only consider the transactions that have not been aborted when we try to serialize them. Okay? So if we don't abort some transactions, then the transactions that do proceed, their effect is the same as executing them in some serial order. Okay? And this is a deep subject. I go into this a little bit when I teach graduate course in collaborative distributed systems, and this is a concept that is taught in depth in database systems. Okay? But this is a very, very important practical concept nowadays. It's always been, and it's certainly relevant even today, okay, as we put more and more things in the cloud and have the data shared. So it is possible for concurrent transactions to be serialized without aborting any, depending on what reads and writes. So we have again, this all that I'm talking about is actually backed by an implementation. So we have non-atomic, atomic, and serializable. So and this the consistency mechanism can be different from the synchrony mechanism we use. Okay, so that's orthogonal. So synchrony determines when we send positive values based on accept notifications. So we can have our single writer synchronous mechanism where one proposer went through two phases. It first sent accept requests and then got accept responses. And once it got the accept responses, based on those responses, it went and sent learn notifications. And now what we do is, to allow multiple proposers, we make them all go through some central proposer. And one of these proposers could itself be the centralized process. Okay? So that's the situation in centralized synchronous. And we can also have centralized asynchronous, okay, where we're saying, look, we don't care about having what we don't care if there's eventual consistency and not non-eventual consistency. And we saw two forms of non-eventual consistency: pure synchronous and synchronous. So we don't care about when values get consistent as long as they eventually do, but we do care about the values being consistent. So we will go and route all the messages through one process. Okay, so both are possible. So let's go and see this algorithm at work. Again, let's take the situation where we are trying to figure out what the meaning of life is. Okay, and initially the value is 0, and somebody proposes 29. Okay, that's site 2. The value becomes pending. That value goes to process 1, which is our central process, which can also propose. Okay, so it gets sent to that process, and that goes and does a remote propose. Okay, which means it proposes on the behalf of 2. It can also do a local propose of its own. So its user might also, before the value has been committed, might go and propose a different value and says, no, meaning of life is 42. So the value becomes pending here. So we have 2 concurrent proposals and 2 pending values. The values haven't been sent to any other process so far in accept notifications. So now this proposed 142 is echoed through a remote proposed 142. So this is asynchronous. So, okay, sorry, we're not accepting here. Okay, so I guess the pending value doesn't really matter here. I guess I've shown it to you, but it doesn't really matter. So we go and make this value 42. And as far as this is concerned, we've reached consensus because this is asynchronous. And the value goes to every other place too. And they become 42. Then 129 goes after that, and the values become 29. So eventually all the values converge. Okay, and like I said, this particular state didn't really make much sense. Now it's going to make more sense. Again, the same proposal, pending value again, same echoing, again a concurrent local proposal, pending, and echoing. Now an accept notification is sent. Okay. It goes to everybody. Another accept request comes in, is sent. Okay. And now the question is, should the second pending proposal be accepted or not? Okay. And if we are talking of serializable, then the answer is no. But if we're just talking about atomic, then that's fine. Okay, because we don't care about as long as the commands get executed in the right order, in the same order, we are happy. Okay, so this is atomic. It's atomic if we accept it, but it's not serializable. Okay, and in this case, it's not serializable. So let's try to figure out why it's not serializable. Let's try to understand this. So I'm saying that should the second proposal value be accepted, and if the answer is yes, then it's atomic but not serializable. Okay, and like we saw earlier, that what is serializable or not serializable depends on the commands. I'm going to argue that if you're talking about this meaning of life being changed, this is not serializable, and it's a subtle reason why it's not serializable, because this is not the delete and remove delete and change case that I showed earlier, where the delete and replace action, because the replace action just doesn't make sense. It does make sense to go and overwrite a value. So the command will succeed. We won't get an exception, but semantically, we haven't got serializability. Okay, we've got a state that didn't throw any exception, but we did not get a serialized state. So what went? Why is this not serializable? So we are assuming, it depends on what you assume. Okay, if you assume that the second proposer doesn't care about what's been proposed so far, the second proposer saw that the value was 0, knew that the meaning of life couldn't be 0, so proposed 29. Okay, but if the second proposer had seen 42, I don't know who the first one, who the second was. Let's assume that the first one is 42 actually. Okay, so if the 42 is the first value, has been proposed, then and read by the proposer, then that proposer might say, "Huh, 42. Yes, I remember. That's the hitchhiker's value, 42. So I will not propose 29." Okay. So this is not equal to executing them serially, because if the transactions had been executed serially, the second proposer would see the result of the first proposer's action, see that it's 42 and not propose 29. But that's not what happened. So this is not serialized. Okay? Again, this requires some deep understanding of serializability, but I'm giving you a flavor of what that means. Okay? And that's why read and write operations both make sense. And we assume here that what the proposer of 29 does depends on what the proposer reads of that object that the proposer is changing. Okay, so let's look at this algorithm in actual code. Okay, so we may or may not have a centralized algorithm. Okay, the algorithm, I've got actually a suite of algorithms that are implemented. So if it's not centralized, we will do whatever we do for a local propose, which we've seen before in our previous. Otherwise, we will send the propose request to the centralized process. Okay. So this will result in remote propose being called in the centralized process. And if we are looking at serializable concurrency control, then we check if some other proposal is pending, and if it is, we go and declare a concurrency conflict. Okay? And we send back that value to the proposer without sending accept notifications, accept request to everybody else. Otherwise, we just do local propose, okay, which goes and sends the value to everybody else. So we take somebody else's proposal and make that our proposal. Okay. And the local propose can be synchronous or asynchronous. So this shows us actual traces. So 42 is proposed. That request is received by the central guy. So there was remote proposal request sent. It's not proposal request sent, but remote proposal request sent. That's received. Another request is received while this value is pending. So that proposer gets the value concurrency conflict back. And we'll see what this came prematurely. So we'll see what that means later. So the first value 42 achieves success, okay, in the manner we've seen before. And so we've got consensus. And now we get another 29. Okay. And this 29 does not result in a concurrent operation conflict because this is reproposed after reading 42. Okay. But as it turns out, we can deny that request. So somebody can say, no, I know 29 is not the correct value, not because it's conflicting with 42, but just because it's a bad value. Okay. So we can get a service denial. So the accept requests can be followed by success, or they can be followed by failure. And the failure response can come because of concurrency conflict or because just the value is not acceptable. Okay, again with the Travelocity case, we just don't have a reservation for you. We don't have space for you. Okay. So this is proposer 2. They proposed 29. They got a concurrent operation, and then they went and sent another value after getting 42, after seeing the success of 42. Okay. Okay, and get proposal service denial. This is accepting acceptor. So this is an acceptor now. They get success with 42, and this is the rejecting acceptor 4. They're the one who gave the service denial for the second 29 that was reproposed. Okay, so the algorithm I just explained to you is the two-phase commit algorithm. Okay. This algorithm was proposed by a guy called Jim Gray, who was at Tandem, and I think he might have won the Turing Award. And he lived in California. He worked for a company called Tandem. And one day he went out boating on the bay and never came back. So that's kind of a sad story. And nobody's ever figured out what exactly happened, but obviously something bad happened. But this is Jim Gray's two-phase commit algorithm. Okay. So, we've got now multiple writes. So what more do we want? Okay, that's the question we'll try to answer now. And so this is my question, and you guys have kind of seen the problem earlier in questions I've asked you, but let's go and see this problem in more depth and see how we can solve it. So what's the problem with this solution to the multiple write problem? Okay, and if you find the problem, and what might be a solution to the problem you might see with the solution I've given so far. Okay, so right now we're saying that everybody goes to a specific process, and that process echoes the results back. And what might go wrong here? And many things can go wrong, of course, or something really bad that can happen. Coordinator may fail, okay? And this is, like I said, Byzantine, non-Byzantine failure. What Andrew mentioned and what David was also talking about was so we are talking of failing meaning just dying, not doing something wrong. What David talked about was doing wrong because of accidents, and then what Andrew talked about was doing wrong because of being corrupted by the controlled by the army. So that's Byzantine failure. We won't consider that. Um, that is a topic in its own right. So when I was a grad student, I spent a whole semester in a distributed algorithms class talking about Byzantine failures, and there's some neat results there, but we won't talk about them. So we want to dynamically choose a new coordinator. So how to choose new coordinator, and how to recover coordinator state. If all we had was this problem, things would be easy. But this is the harder problem, which will require us to go in great depth into another algorithm called Paxos. Okay. So switching central replicas, the consensus problem, the solution we gave assumed that if A sends to B via C and B sends via D, then C is equal to D. Okay, so the central replica is unique. So we need non-centralized algorithm during switchover as no common central replica to solve consensus problem. So we have a recursive problem here, and we need a solution that is not centralized, because our centralized algorithm, we don't want to recursively call ourselves. Okay, so we can use the algorithm that I just mentioned earlier, Paxos, to do this. But since we haven't seen Paxos, we'll just assume a simple algorithm where we just have 0 phases and we order the replicas by, say, ID. Okay, in the army, as Chris mentioned, we could have a promotion order and pick the next one in the list, a chain of command kind of situation. Okay, so in the code that I implemented, there's always a get server name. So if that server name is null, and it'll become null if that other server has failed, because we'll get a message. Then we just look at the sorted members we have, the current members, and we get the 0th element of that. Okay. Okay, but otherwise, if sorted list is not sufficient, then we need some other algorithm, non-centralized algorithm, and I mentioned an algorithm called Paxos. And to sort of show you traces, I actually did something bad. I killed the process not when it was doing nothing, but I killed the central process when it was in the middle of sending learn notifications. Okay, so let's see what can happen here. So uh, so this is the process. It sent the remote propose request sent, and it received it also. So it is both the proposer and the central process. It sent an accept request, and it received one accept request. It also received a right. It received its own request. It sent its own notification, and then it also received another uh, proposed request from another process, and then it died. So this is really bad. Okay, the first value hasn't been resolved, and the second value has been proposed. Okay. So the second proposer gets to know that the first proposer, that the centralized process has died, and for some reason this message arrives twice, and it goes and uh, so this is, it sent this value, it got this message that the process has died. So it goes and sends the value again. Okay, and it receives the value because it's the second and next in command. Okay, and then this can go on and it can get a denial. Okay, and here this other proposed, this acceptor gets also the message, and gets the service denial message from the second central process, and this process also gets to know that the original process died, and gets a denial also for the second value. Okay. So yes, we can transfer control, and if things were not pending, things would, if the central process died while not in the middle of processing a transaction or an action, then things would be fine. But what can happen is that this process might die in the middle of uh, achieving consensus, and that's bad. Okay. So what if it died at this point? It just sent some learn notification, not all, and things can get really messed up. Okay. So that's the interesting part. If it has sent no state at all, it got the message, but it did not tell anybody else about this message, and it dies, it's as if it never received the message. Okay. If it sent all the information it needed to send and got all the responses and waited till consensus, things would be fine. The problem is that it sent some state to other processes and did not send the state to other processes. Okay. So we are now in an inconsistent state. And the question is, how do we solve this problem? Okay. And the key will be to get rid of the central process entirely. And the key is to recognize that if you have gone and sent state to other processes, then those other processes can help restore that state. Okay, the state is there in some set of processes, and those processes can together decide on what should happen to the proposed value. In other words, we don't have a central process. We do have an accept phase, but the answer that we get from the accept phase is determined by not one process, by multiple processes. That's another way to say what I want to get to. Okay? So somehow you want to distribute the algorithm. And so let's see what I have next. So we have inconsistency, and new sequencer may be arbitrarily behind in general. So that becomes a tricky issue. But the key to solving the problem is the correct state is with at least one alive member, and that member could be used to restore the state. And if it's with multiple members, together these members could be used to resolve what the correct state should be. Okay. So if we try to go in, so actually I'm going incrementally to the algorithm. So correct state is with at least one alive member, so we can see which member is the most advanced and elect that member. But that member may die in the middle of switchover, and that's why we want to just try to not go to the centralized route at all. Okay. So this is where we want to use the voice of more than one member. We want a more democratic or parliamentary scheme than a monarchy. Okay. So our remaining problems are that if we don't have a sorted list, we need some non-centralized algorithm to decide who should be the next centralized process. Okay. And different consensus states possible even if ID is used for switchover. And in general, we could use the voice of more than one member. Okay. So what we're going to do is we're going to go to Paxos, okay, and we're going to try to figure out how we can do. So the question we're trying to answer is how to detect and sequence concurrent requests. And the algorithm we've seen so far is, like I said, an autocracy. And we want a democracy, we want a parliamentary system.